But no, we're talking about Phoenix 1.2, kind of what I've been doing for the last 6 months and what I want to do from there on out. But before I talk about where we're going, I want to talk about where we've been for the last 6 months. We had a couple big milestones. One was the Phoenix book. Yeah, it's out, and yeah, thanks. And Prog is giving a 25% discount for this conference. Go to bit.ly/PhoenixBook. You can use ElixirConfEU 2016_Phoenix, which no one remembers. So like, someone tweet that out. But this was a ton of work. It took about 8 months. I wrote this with Jose and Bruce, and super excited to have it out. And I think it's important to have first-class learning materials for the community outside of our kind of the basics, the online guides. So I'm excited to see the reception so far. So check it out. And then also the brag slide that we'll hear about later from Gary. But we had a huge milestone with 2 million channel clients on one server. And not only is this amazing from a marketing perspective, but it's also just incredible because it proved what I hoped and what we've been saying all along, that Phoenix and Elixir give us this crazy performant environment, but we don't have to sacrifice our productivity. So we have this channel layer that abstracts WebSockets, that abstracts long polling. You have this really nice API. You don't have to worry about how's the client connected, what happens when the connection drops, how do I notify clients if there's a crash on the server but the connection's still good. Like all these things that take work, we're able to take care of for you but still get kind of world-class performance. So that's super exciting, and the only reason it leveled off there is because I misconfigured the server. But we'll hear about the whole story of how this happened and what led to these charts here from Gary later on. And I want to talk about kind of the growth over the last, since 1.0 last year. We're seeing about 4,000 downloads a day from Hex, which is hard to quantify, but during ElixirConf US late last year, it was about 1,000 or 1,500 downloads a day. So occasionally I just check that download number and I'm like, oh, wow, we're like 4 times where we were just several months ago. And I'm told that there are focus books in the works around using Phoenix with gaming, like we heard from Keith, working on a book for Phoenix and Phaser. There's Phoenix being used with embedded devices. So I want to dispel this myth that people will ask, is Elixir have a life outside of Phoenix or outside the web? And it's like, of course it does. But it's an absurd question to ask just because Phoenix is kind of redefining what is a web framework. Because it's not only just about building browser applications. We're already seeing Phoenix used in these areas that you wouldn't typically think of a web framework. So I think we need to dispel this myth of, is Elixir only good for web? It's like, no, Elixir is amazing for pretty much anything connected to a socket, but Phoenix just gives you a nice window into your greater Elixir application. So I'm really excited to see kind of Phoenix used outside of the standard web application space and where that's going to go. And we're also seeing job opportunities. So there's a lot of the Hacker News Who's Hiring thread this month had 5 Elixir-related jobs that mentioned that they're using Phoenix for API backends and channel applications, kind of really interesting use cases. And I think it's showing that companies are actually really using this and making money and hiring people. So that's really exciting to me. But Phoenix 1.2 has been kind of what has consumed my life for the last several months. And it's out today. I feel like Steve Jobs, available today. It's actually been available for a week. And as far as I know, we don't have any working bugs. So as soon as Ecto 2.0 goes stable, Phoenix 1.2 will go stable unless someone reports an issue. So please don't. But the big feature of Phoenix 1.2 is really Phoenix presence, but we also have some other changes. Lib is reloaded in development now, so there's no longer this question of do I put things in web or lib? It used to be, well, if you want them reloaded in development, put them in web. So really the answer from now on is just put your Phoenix related files in web, and everything else goes in lib like any other part of your Elixir project. And we're exploring changes in the future to maybe the web directory can just go back inside the project. Now that there are changes to the Elixir compiler that allow this. And then we extracted Phoenix PubSub. So Justin asked me for a number of months to please extract Phoenix PubSub. So he didn't want the web dependency of Phoenix, but he wanted the PubSub layer. And we finally have extracted it, and we included Phoenix presence within Phoenix PubSub. So you can get this distributed PubSub layer, but if you don't need the web portion, it's now a separate dependency. And then obviously we were able to focus on Phoenix presence, which was the kind of defining feature. So I'm going to talk a lot about Phoenix presence and a lot about conflict-free replicated data types, which hopefully I can kind of give some insight to how they work. But then I was thinking last night that it's the first talk of the day, so I'm surprising everyone with how CRDTs work at 9 a.m. So we'll see how it goes. But it seems like a simple problem, so I want to get down to the nitty-gritty details so we can appreciate what we have back up in user land. Because when you think about presence, at least when I was thinking about how to solve this problem, I don't know where Jose is in here, but I think Jose and I were like, hey, people aren't solving presence correctly. Here's how it would correctly be done. We hopped on Skype and we're like, we'll write a blog post. Like, we don't need to make a feature in Phoenix. We'll write a blog post on like, oh, this is how you would do it correctly. So we hopped on Skype and it was like a 3-hour Skype conversation that started with, okay, what are we gonna say in this blog post? And then there were so many edge cases and it became like hours long of like, oh my gosh, this is like a really hard problem. So I'm gonna walk you through that. So at first you're like, here's what we wanna solve. We have users connected from 2 different browsers or 2 different devices, and we wanna show like on our web browser, hey, which users are online. So like just display a list on a browser tab was the problem. Like, oh, this couldn't be too hard. But it's more nuanced because there are a couple features of presence, like what does it mean to be present? Because if user 1 opens 3 browser tabs or logs in from their browser and their iPhone, that's 3 distinct presences for the same user. So presence is really defined as like something like a connection for each of those users. So we need a way to distinguish that because the client might say that, you know, I might want to show an icon, say, on the browser tab saying I'm online from my iPhone, but what takes precedent? Or I might set my status to online or away, but on my desktop if I'm online, but if I set my status to away on my phone, who picks what? So you need the ability on the client to figure out priority. So it's a little more nuanced, but that's like the easier problem to solve. The harder problem to solve is the distribution problem. And this is an issue, I think, at large where people will come into Elixir and they'll develop something on their laptop. And we have really nice primitives like agents and gen servers where we can put state. So what we had seen users doing is they would have someone join a channel and then they would just push that user into a named agent. And it would work beautifully on their laptop. But as soon as you deploy that, you now have like a presence agent running on separate nodes. And anytime you ask for that state, you would just get the users that had connected to that node. So this is a problem. And at this point, most other recommendations from like other libraries and frameworks that we're seeing with similar features, they'd say, I know how to solve a shared state access. We'll just deploy Redis and put it in a database. And we have solved all problems. And I think Redis is a great little piece of technology, but I think inferior platforms, they push us to these crutches, and we just think like, oh, we'll just put Redis, and we're done. And I think does a disservice to at least Elixir and Erlang because we have this amazing platform. So presence is ephemeral state. It's state about a user that is currently connected, and as soon as they're not connected, that state can be thrown away. So we have ephemeral state, and the language has an amazing place to put ephemeral state, and we put that in processes. So there's no reason for us to deploy Redis because we have a single point of failure now. Our operations overhead is now we have to figure out where to put this thing. It's going to be a bottleneck, not only because we have to send all traffic through it, but we also have to now deserialize and serialize the data in and out of Redis. But if you accept all those deficiencies, if you say, okay, like, you know what, it's going to be fast enough, it's going to work for me, you're still missing a key point because it appears to be solved. And this is like the best case scenario of what other recommendations are doing. There were like blog posts on like, okay, when a user logs into the application, we'll just put them in Redis. We can detect when they leave and we'll remove them from Redis. And this is really the best case scenario that I've seen from other solutions. And it seems to work. Like the presence list we'll grab from Redis, and now we have shared state, no problem. But almost no one solves the issue we heard about yesterday with like, you know, computers suck. So node 2, let's say, catches on fire. And now what do? Because we have written data into Redis, and the node that was responsible for cleaning up those users that are now disconnected because the node died are just going to be orphaned forever. And most people just say, well, this is not going to happen that often. similar to what we hear with people coming like, oh, the network, it's mostly reliable. We don't have to worry because the network's fine. So we can ignore this problem, or we can actually say, let's solve it properly. And this is what we want to do with Phoenix Presence. And we can do that with a CRDT. And I'm going to try to break down, not teach any maths, but at least give you a mental model about how to think about CRDTs and why we have the constraints the way that they are, and how this makes us, kind of changes our thinking about when we have distributed systems. There are just certain facts of life, certain truths that we can't ignore. But CRDTs give us strong eventual consistency. So it's something that as long as all nodes receive all messages, will eventually come to the same result. And that gives us conflicts that are mathematically impossible. So the goal is we don't want to have a distributed consensus protocol or global locks. We want to be able to just send messages. They can arrive out of order. They can arrive multiple times. And we can still remotely synchronize, but without actually having to lock the cluster or rely on a central database. And there are a bunch of different types of CRDTs, but there's a paper here at the bottom that we base our CRDT on. And this is where I started out this process like, oh, CRDTs, this is going to be so fun to learn new things. And I started reading this paper, and I entered a stage of like crushing self-doubt. Because this is just a random sentence that I lifted out that it's not even saying much. So it wasn't even like the grits of what the CRDTs are, but it's like, if you read this, it's like, in this way, for each replica, there is a monotonic sequence of states defined under the lattice partial order, where each subsequent state subsumes the previous state when joined elsewhere. And I'm like, what is this? This isn't even talking about maths, and I can't even comprehend what they're even trying to convey to me. And it's not the fault of the authors, because this paper is like the basis of a really great research and really great ideas that we put into presence that we wouldn't have been able to do otherwise. But I think there's an issue with like academia is using, like, they're coming from a math background, very theoretical background, and I just wanted to know, like, please help me implement this. Like, how do I turn this into code? But it gets worse because like I was like, okay, I'm gonna keep reading. Maybe it's just gonna start clicking, and then like a paragraph later, they prove something with math, and then literally they're like, proof, trivial, and I'm like, what? So it was like crushing self-doubt phase where I was like, maybe this is too much. Like maybe I'm going to be unable to accomplish this. And this is where Alexander Sanj, who really was instrumental in helping with our CRDT implementation, he gave a great talk last year at ElixirConf about CRDTs. He kind of had multiple Skype sessions with me to break down like what this lattice partial order, subsuming states, and like turn it into words that are just like English that makes sense. And then it was like, oh, this is like, you can actually put these in terms that are just real. But I was still thinking through this process that like, I'm going to be unable to achieve this myself. Like maybe I've I've tried to take on too much. And I have to pay credit to Jose, and maybe this is a quote, but it's something along these lines where I was having this crushing self-doubt phase, and I literally like asked him, like, maybe, like, is this crazy? Like, maybe try and implement this CRDT thing, like, maybe we should just let people figure it out, or just use Redis. Like, maybe I can't do this. And he just made a comment like, no, you can do it. Just matter of fact. Like, nah, I think we're fine. And, but the crazy thing is, I think this is a testament to Jose, that I was like just that little nudge, and it was like in the back of my head, like, oh, maybe I can do this. And I took like I had a 3-day weekend, and just that little extra nudge of like removing that little bit of doubt. Like I went back to the paper, using also Alexander Sanj's example implementations we have been working on, and in like 3 days, I could actually digest and understand the paper. So it was just like Jose changed my frame of reference a little bit. I think that's kind of a testament to how he's helped everyone in the community level up, where it's just like, instead of trying to make this insurmountable problem, it's just a little nudge to say like, no, I think this is possible. So now we get to learn about CRDTs, but no math and no subsuming states and partial orders. I just want to give you a mental model to think about these problems. Like why are these necessary? So we're using a or SWAT CRDT, which is like, all of these words are going to be like, why did they pick these? But Or swap, it'll make sense in a moment. It means observe remove set without tombstones. It's a type of CRDT. But ignore that. So let's say we have 3 nodes. And we want to say which users are online. And these nodes have different states at different times, and they need to synchronize and replicate this. So let's see, like, why is a CRDT necessary? So in nodes, let's say we have 3 nodes that start out with a state. And the nodes are going to send sets over. It's a observe remove set. So it's just a collection that has no particular orders, and it's going to hold users that are online. So node 2 is going to replicate saying, hey, here's my set. Everyone's going to merge that with their set. And node 1 is going to say, hey, I've got user 1 in my set. And then let's say node 3 is going to get this first. Because we have a network, we can't defy the laws of physics. There's going to be the speed of light. There might be some packet congestion. So let's say that node 1 replication at the top is still in transit. Node 2 has not received it yet. But what happens now if node 3 says, you know what, I'm going to remove user 1. I'm going to replicate that. So now we have inbound sets to node 2 saying, hey, I have user 1 in my set, and hey, I remove user 1. So now how does node 2 act? Like, does it discard or add user 1? And the answer is it just depends on when it arrives. And this is a problem because now we have no consensus. If it arrives after we get the message from node 3, we're going to add user 1 to our set, and now we have a global conflict. So these things are supposed to be impossible, but this is an issue. So how we were going to solve this, or how I thought we solved this initially, was like, oh, maybe we can just like timestamp each message. It was like my naive thinking. Like maybe a timestamp, and node 2 can say, oh, if I have a conflict here, I can look at the timestamps and figure out, which should have been added first. But this turns out to be like the worst question to ask in a distributed system, because it turns out that there's bad news that like time is an illusion in a distributed system. Like you have to totally change the way you think about time when you're thinking in a distributed system mindset. So I was like, okay, if I can't really apply wall clock time. I can't just put a timestamp on things because I come from like a web background. It's like, oh, we just have a timestamp in the database and problem solved. But we have to come up with new ideas. And this is like Alexander Sanj. I have some quotes from him where like I would ask him questions like naive questions, probably, from a CRDT point of view, saying like, well, why can't we just like, why do we care about things that were removed from the set? Why don't we just keep the things that we have, and that's all we need? And then he would say like, the past will always come back to bite you. Like you can't ignore the past. But I would be like, but if we can't ignore the past, but we can't have time, like what? How does this work? So it's just a really interesting learning process. So it's like, how do you model a system without time? If like, how do you resolve conflicts if they're going to be dependent on when they happened in the past? And I couldn't really think about how this would work, but I found this graffiti here, like time doesn't exist, clocks exist. So it's just this like thing that we use, but we can say there is a solution to this. We can say time doesn't exist, but vector clocks exist. And vector clocks is the answer here. And this is one of those other words that, like a year ago, if you would have asked me about vector clocks, I would have said, like, ooh, that sounds really academic. It's probably something I don't understand. But it turns out, at least conceptually, it's pretty simple. Vector clock is just going to be an integer value. And it's a way for a node not to record its server time that it perceives, because that server time could be different. Even if we try to synchronize server times, we could have clock drift, like Erlang now, this in pre-Erlang 18 would actually drift your clock. So servers cannot rely on their actual clock time being set, but we can just say, well, if we can identify a node with a tag tuple, and it's just going to use an integer value, and instead of having a specific timestamp in history, it's just going to represent some change that I've had. So if I experience an internal event that has changed me to go from one state to the next, I'm going to bump this integer value. And if I experience another internal event, I'm going to bump this integer value. And that's all vector clocks are, essentially. And in this way, we don't know the wall clock time that happened in the past, but we were able to actually see that something had caused this node to go from one state to the next. So we're able to at least have, we like to say, like a causal history, which is another word that I was like, causal, but we'll see in a moment what that means. So the idea is now we can ship a vector clock with each element in the set as we're replicating information. So instead of just sending the raw set, every element in the set will get the vector clock. And anytime we add or remove something from the set, we bump our clock. So we'll have unique kind of tag tuples sitting along with each element in the set. And now if we have this conflict here, where node 3 says, I'm going to remove user 1, but during transit we have a user 1 that was added, node 2 can actually look now and be able to distinguish, I have this clock here for user 1 from this node, but node 3 says that we have a tombstone here. So that's where that crazy word comes from. Node 3 removed the data about user 1, but it kept its vector clock in its set. So now node 2 can look at these and say, oh, node 3 has seen that tagged value, so that means it must have removed it from the set because it has the tombstone. So we're able to resolve a conflict here with vector clocks. But it has a severe limitation in that the only way we can resolve these conflicts is if we keep tombstones around. And remember I told you that we have an observe remove set without tombstones. So tombstones can't be the solution. Well, they can be. If we have an infinite memory, tombstones are great. We can just keep a tombstone for every user that we remove until the end of time, and then we'll be conflict free. So like every time we remove a user, we would just add a tombstone, and we could look at those tombstones. But obviously that doesn't scale. So this is where part of the paper and part of this data type says that we can apply an optimization here. That's kind of neat. So it's like as users are removed or elements are removed from the set, we will keep tombstones temporarily. And after we merge sets from another node, we can just sort the vector clocks and we can actually compact all of that information. So imagine I had this set here and I could say I'm going to sort it. And I can look and say, look, you know what? I've seen node 1 from vector clock 1 to vector clock 3. Or in a real system, vector clock 1 to a much larger number. And that means I've seen the causal history of the causes that have, the effects that node has gone through from that range. Since I've seen all that, I can just delete everything between there that was a tombstone, and I only have to keep the relevant information of users still in the set. And a separate map of the causal context. So the context of the causal history of this node is just going to be stored in a map for the cluster. So this is like extremely efficient compared to what we had before, right? We can keep just the elements that are still in the set plus an extra map saying, okay, I've seen node 1 from 1 to 3, seen node 3 all the way up to 4. So we just keep these single key values around for each member on the cluster, and then our set remains finite in size. And that's how we're able to get the without tombstones part of the observe remove set. And then the observe remove part just means that anytime we're merging a set from another node, we can just walk our set, look at our causal context, and if a node doesn't have a member that we have in our set, but it has the causal history that it should have seen based on their vector clock number, we know it must have been removed. So it's a really interesting data structure and very hard to understand, especially from the academic sense. But once it's explained in English terms, hopefully you have some frame of reference to think about this thing. So now, wipe that from your memory. That's how OR SWATs work. But the whole reason I wanted to go through that exercise, one, I wanted to pay it forward to if you're trying to understand these things. But two, you don't have to think about it, right? Like the whole goal is like now even I don't have to think about it day to day. It's like up in Phoenix land, user land that you're going to call, it's like as trivial as can be. So if you want to track users that are online in your channels now, it's like 2 lines of code. After someone joins, we can just say presence track. So track my socket, it's going to use that socket's topic. I have some user ID that I want to keep track of, and I can even store metadata about that user. Like maybe I've set my status to online or away. Maybe it's going to be information about the kind of device I've connected with. And then I can just push all the presence information down the socket and show that on the client. So like 2 lines of code on the server. The fact that this is happening with CRDTs we don't care about. And then on the client we also have a new presence object. And it's just as trivial. It's almost like a CRDT on the client as well. Where we can say if we get some initial state, we can call presence sync state. And this is going to resolve conflicts because in between disconnects we're going to be reset the whole state, but we already have some state held internally. So it's going to sync that up properly with the server between disconnects. And then anytime we get any kind of users coming and going, we get this special presence diff event. So instead of, like, as data is replicated across a cluster, let's say 500 users have come and gone, we don't want to send that as 500 events, right? That's much worse for the server, and it's much worse for the client receiving all this data. So instead, that we'll get a single event of like chunked diffs. So that will have like 200 joins, 200 leaves. And we have this sync diff function. And this is just going to sync this with a JavaScript object on the client, but you can also pass callbacks here to say, okay, has this user joined from a device for the first time, or maybe they just joined from a second device? So we give you callbacks, be able to display it. If I log on for the first time, I want to alert everyone. But if I log on if I open up new tabs, I don't want to always keep flashing, Chris signed online, so you can detect that. And then you can also figure out strategies for listing presences. By default, we'll just pick the most recently joined user. So if I'm online from 3 different places, by default, it's just going to pick the most recent one. But you can pass a function here to list that will say, maybe pick one that is showing you as away, that will take priority, or maybe pick one that is using some custom priority about maybe mobile takes precedent. We give you those abilities. But at the end of the day, it's a few lines of code on the client and server, and this just works. You don't have to think about, oh, is this going into Redis? Is this going to scale? What happens if a node goes down? Like, everything just works, and it's just a few lines of code for you to use to solve something that you have in your app day to day. So I kind of want to drive this point home with a demo. So I've got an application running here on 2 nodes, and we're just showing a list of users that are online with pretty much identical code with a little bit of bootstrap to make it look pretty that you saw on those last 2 slides. So on the left and right, I have port 4001 and port 4002 with nodes clustered together. I'm going to clear my scroll back here. So I've got these 2 nodes. They're running on my laptop, but they could very well be on a data center separated over the wire. So let's see like kind of the basic features. I'm going to add a new user to node 1, and I'm going to name it Safari prefetches the page, which will like troll me because someone will show online and it will look like a bug. So I need to use a paste buffer so Safari won't prefetch this and show a user is online. So let's say that Justin is going to be online from node 1. So Justin, and I just can pass a name as a URL, so it's easy. And you can see it replicated that information almost instantly. And we'll try to replay that. But now Justin is online on both nodes. And since he's online locally on node 1, that node 1 got that information instantly. So I'm going to close Justin's tab. And if we watch, we should see him disappear from the left-hand side. And then probably within a second or 2, he'll disappear from the right as that remove is replicated. So I'm on Chris's tab. I'm going to close Justin's tab. He'll be removed instantly, and then should be removed from the right in about a second. Gone, gone. And that was actually super fast, but we happened to catch the heartbeat cycle like right away. But this is just being replicated. There's no like central place that we're like asking like Redis, like, hey, what's the user list? This is just happening, which is nice. But we also can detect multiple users. So let's say Jose opens up a bunch of tabs. So now it says, okay, Jose's online from 3 different places. And this is just that optional callback. I can say, given all of Jose's presences, just add a count to that list and show that online. And as I close these tabs, we'll see this decrement like instantly. 2, 1. So we've solved those problems, right? But we've solved the most difficult problem is, what if we have a net split? Or what if a node goes down? So I'm going to clear the scroll back here. And let's say that I'm going to simulate a net split by disconnecting these nodes. So I'm going to disconnect from node 1 at 127.0.0.1. So those nodes are disconnected. So what happens? Oh, what happened? So like those users became unreachable, and as far as each node was concerned, the other node is gone. It must have died because we haven't heard from it. So what we wanted to have happen on the front end was not that orphan data. We wanted that to just, those users are gone, right? So that was cleaned up for us automatically. We didn't have to do anything. And we have some verbose logging enabled. If I bump up my font here, and we can see that these nodes detected that there was a replica down. from each node. So you're like, oops, this node must be gone, but they're still up. So like, you want this to happen when a node actually goes down, but how do you recover when you come back up? It's an even harder problem, because now imagine these things are still running, and if I open up maybe Justin on node 1 again, so these nodes are currently running independently, but having things happen that aren't getting replicated. So that's running independently, so we've missed that join. Let's say we have Eric on node 2 now. So now we have data out of sync. Like, this is a problem, because when we heal from the cluster, we can't say, oh, let's just go check Redis now and try to resolve our conflicts. Like, what do we do? Especially if we had 100 nodes. So with net split recovery, let's see what happens now. Instead of node disconnect, I'm just going to say node connect. Oh my gosh, it just, the users are back online. Like, we didn't have to do anything. This just recovered for us. And the client just got that information. Like, there was no extra code on the server that you had to write or on the client, JavaScript client, to say like, oh, what happens now if this recovers? Like, it's literally the same code. And the cool thing is watching the logs, like what happened, like how'd that work? Well, we can see, maybe, with the font that there was a replica up detected. So node 1 said like, hey, I see a replica that came online from node 2, but I've previously seen it. I didn't mark it as down permanently. I said like, well, I can't see this thing, so I'm going to assume it's down. So both nodes detected that the other one had come up, but the coolest thing is then they looked at their vector clocks and they said, ooh, I miss information from you. I can see that from your vector clock now, from what it was before, you must have had internal events that caused you to change. So they will send a transfer request. So we can see, if I blow up this screen, node 1 received a transfer request from node 2 saying like, hey, catch me up, give me Justin that I missed. And then node 2 sent its CRT over saying, okay, I'm going to catch you up. And both nodes went through that process, sending their CRDTs across. And this works for the case of a new node coming online as well. So not only net split recovery, but you also have the case of, what if a new node joins a cluster? You're trying to scale up, you provision a new instance, like where do you read that information from? Because if you have 100 nodes out, do you ask everyone? Do you ask all 100 people, give me all of your CRDTs? So for a large cluster, that's a problem, because if you have to ask 100 nodes, and we have to send the 100,000 active users across a cluster all at once, we're going to like flood the network, we're going to flood that node. So let's see what happens if we start up a node on another port with another name, let's say node 3 here. How is it going to get those active listed users? Like, hey, both of them detected that there was a replica that came online. And notice how it asked for a transfer request just from one node. So node 3 sent a transfer request to node 2 this time. And node 2 said, okay, well, I'm going to send my whole CRDT to you because you need everything. But it didn't have to ask node 1 for anything. And if you go to the browser for node 3, maybe with name Max, all those users are just there. So it was able to look at it sampled the vector clocks on the cluster when node 3 came online. And it said, okay, I only need to ask node 2 in this case for information. And because I can see the causal context of node 2, I know that it must have seen everything that node 1 has. So I can ask the minimum amount of nodes to give me information instead of asking everyone. And you don't have to think about that. Like you have maybe a frame of reference to appreciate it now with the CRDT, but like all of that is taken care of for you. So at the end of the day, it makes your life much easier. So that's Phoenix Presence. I'm super excited about it, and check it out, use it, and please report your experiences with it. But as far as we know, we have no working issues. So we're super excited to have that and just about ready. But I want to talk about maybe what's next. Maybe. I talked about this at ElixirConf last year, and we had some ideas, but those have kind of gone on the back burner because it turns out that I may have accidentally accomplished my goal from the beginning. If you've seen the very first ElixirConf talk, about my very first talk on Phoenix, I talked about like, okay, I think Phoenix is a distributed web services framework is what I had on like my first slide. And like maybe in the far future, I would make this like service discovery thing. And like I had no idea what I was talking about. Like somehow that would be, but I knew the platform could do it. Like I knew that that would be cool to be able to just say, I've got these services on the cluster and I can discover them and ask them to do work for me. And in the back of my head over the last 2 years, I've been thinking I still want to accomplish that. And people would ask me so how's that, what's the progress on that? And I'd be like, well, that's way off. But it turns out we accidentally did something pretty neat. We solved the problem accidentally. It turns out we can build on top of presence to get this. We're suddenly we have this vast untapped potential because we started out with this trivial problem. I'm I want to show a list of users that are online was how we wanted to start, and somehow we ended up with we have service discovery accidentally, which is really neat because I thought it was going to be a lot more work. But let's see how that works, because we talked about the CRDT and users that are online, sending data back and forth. At some point in this process, it was quite far in. We were like, you know what is the difference between sending sets of users and sending sets holding services? Instead of saying this user's online, it's really just a process that says, hey, I can do user session stuff, or hey, I can send notifications. It's the same exact problem. And we still want those same semantics of no conflicts, being resilient to net splits. We still want all those same principles. And we can go further than that. We accidentally created a distributed process group. And this is not something I realized right away. I think it was Jose that said this is basically PG3. There's the Erlang PG2 library as a distributed process group, and we accidentally made something that is kind of a step above that with some nice features, we can attach metadata to the processes. But let's see how is this a process group? Because the API started out, track my presence on this topic, so hey, this user is now online, and I can list the users later on rooms 11. So imagine instead of doing that, listing a user, their process online, instead of saying which users are in a room, what if I just said, okay, give me all the web crawlers on the cluster? And that would return something with the PID that I could contact, and even metadata what the current work factor, the number of jobs. And I could look at that data and say I'm going to call the one that is doing the least amount of work right now. So we realized there's some really neat features in here for service discovery with the metadata we can store. So the client can actually do load balancing just by looking at the work factor. And this is just there. There's no, this is a real thing that you could do in CNIEX today. It went from topics and users to topics and any process in the cluster. And let's say we could wrap that up in some nicer API, because you don't want to know the details of topics and how that key value works, but maybe you can just list anyone on the cluster that can do web crawling, get the process, send it a message, do some work. And that's just there by accident. But we can do other neat things, because with that metadata, we realized we could do client load balancing, but there might be different strategies you want. Maybe you just want the default to be a random. If I have 3 game servers or 3 web crawlers, I might just want to randomly send. If I detect 3 on the cluster, they're present from 3 places, I'll just pick one at random to send. Or maybe I, by default, shard them. And this is something that we would just do for you by default. So that way you're at least balancing the messages going to them, but as the end user is concerned, you're just saying, well, there's 3 of these things out there somewhere, and I want this thing to be fault tolerant, so if one of them goes down, I'm still going to send a message and have a game session served for me. And we can do that for you. And it's just there. We would just have to write the code that hashes and then sends a message to a process. So in user land, if you wanted to write, we heard from Keith earlier about he was spawning these game sessions. So instead of having to run those game sessions on the local node, we still have the problem of, even if we can globally register a game session, we don't necessarily want to run that on the Phoenix node that is serving the web requests. We just want to have some big box somewhere that can do game servers. And we probably want multiple of them if we want to be fault tolerant. So you could write some API that says, hey, spawn a new game session for me, and you get a process back, just like any other code. But internally, let's say you want to call a gen server, but maybe, and this is just a pseudo API, but maybe we have this thing called service call. Give it a module, and this is going to do the service discovery on top of Phoenix presence, and by default, it's just going to shard, saying if there's 3, I'm just going to pick one so it's well balanced. And it's just going to do that call, and you're going to get a response back. And let's say since we have access to that metadata, maybe we can allow an API like this and do custom load balancing based on your application. Where if you say, I've got these game servers somewhere and their metadata is going to be periodically updated with a work factor, which is just something you come up with to maybe say, given the available amount of CPU and memory on this box, because maybe if you shard and you have a giant server and a small server giving the same service, you don't want that to be equally balanced. So maybe periodically the node says my work factor is going to be 0 to 100 based on available resources. And we can look at that from the client and say, I'm going to just do a sort on the services available and pick the one that has the smallest work factor. And otherwise, we can treat it just like a gen server, and we get a process back and we send it messages directly. So that's pretty cool. And this is something that just happened by accident, which is even nicer. So I'm really excited about that. So that, just that API is not necessarily exactly what we'll end up with, but I think that we've got this kind of gold mine of possibilities and something that I thought was way off that's included. So I've had this insight in how did we accidentally do this? And to me, it's a testament to the platform that we started off, how do we solve this trivial problem? And we ended up thinking well, since we have the platform, we have the platform that can do all this great distribution, we can solve it in the ideal way. And we solved it, and it ended up being something far greater than we thought possible. And I think that's not a coincidence. I think the fact that we had the primitives in the language, the primitives in the virtual machine to do this distribution, it's no accident that we ended up with something that was extremely powerful. And I think in any other language, at least that I'm familiar with, I would not have ended up here. I would have ended up saying, hey, I've got this thing that we can use Redis, and it's gonna be fast enough. So it's pretty cool. I think it's a testament to the platform. But outside of that, so outside of those big ideas, we've got some other areas that we want to look into. One is first-class umbrella integration. So maybe having a -- umbrella flag to the Phoenix generator that will just do some niceties for you. Because umbrella applications, I think, are a little underserved in the community, and they take a little bit of plumbing to set up. If you set up the dependencies properly. So maybe by default, if you pass the umbrella flag, we'll generate a web separate application for you and one application for your application domain. And we'll set those dependencies up properly for you, so then you would have literally just an app that serviced web requests that called into your greater OTP infrastructure. And we also want to have more extensible transports. And Sasha is here somewhere. He's done all this work, and we just have to review it and resolve some conflicts that have changed with presence. But we want to have the ability to write transports without a bunch of duplication. Because right now, the way I write transports is really just a lot of cut and paste. If you want to do something similar to the WebSocket transport, but your own custom way, you just have to duplicate a bunch of code. So Sasha has gone in, done some refactorings to make this much better. And we want to focus on new generators that really push you towards better isolation. So generators like the Mixed Phoenix Gen HTML, Mixed Phoenix Gen JSON, they've always been learning tools. So we want to focus on doing really teaching you better. So I don't think there's anything wrong necessarily with our current generators, but we are seeing that Ecto has this idea of isolating the persistence from our data structures, which is great. But I think it's not enough to push people into how do they structure their greater application. So we want to wrap the Ecto code, your repo code, into a module, and just so you can call modules and functions that separate your Phoenix application from the details of how this is happening. And then I also, in the back of my head, like I talked about at ElixirConf last year, I really think we can solve client-server data synchronization. And I think it was probably good that I got sidetracked with presence. Because we are seeing in the community now, there's some new ideas, because this is a hard problem. Meteor has their DDP protocol, and then GraphQL has something they call subscriptions. It's not a finalized spec yet, but it's coming along. And we have folks like Bruce Williams, Ben Wilson, and Josh Price that are working on really great GraphQL libraries in Elixir. So I think if I wait a little long enough, finish service discovery, and then I think there might be a really good story on here's how you would actually do client-server data sync. And we have some things in Elixir already that can handle it. And then at that point, we can say, okay, how do we tack this onto channels and someone else has solved all the harder things for me. But that's still in the back of my head. It's we have the technology. We can solve these problems. So that's Phoenix 1.2 and really what's on my mind. Before I finish, I want to thank DockYard, where I work. I've been able to focus really almost all of my company time on Phoenix for the last 6 months. So I've been working nearly full-time on Phoenix, and that's allowed me to build presence. That's allowed me to go on a deep dive into research papers on CRDTs, and it's something that I would not have been able to do without their support. So I really appreciate it, and if you see them, give them a big thanks. Thank you.
Wow. I, for one, am really looking forward to action presence coming in Redis 6. I think it's time for a few questions. So I'll go now.
So yesterday Keith mentioned the issue where the number of updates you need to send out scales as the square of the number of users you have. How does Phoenix Presence deal with that when you have lots of hundreds of users online or more?
Yeah, so one of the issues, or one of the ways we solve that is with the diff. So instead of, if I replicate across the cluster, especially across a net split, imagine that I've been disconnected for a while and I have 1,000 joins and leaves. And imagine for that, we don't want to put information into the metadata about the user. Let's say we still want the user's name, their current profile information, but we don't want to put that into presence because now we have a caching problem. So if I replicate 1,000 users that have joined, and then I also need to fetch from Ecto or my database layer the 1,000 profile information, it's like I don't want to perform 1,000 queries. So it's kind of a similar problem. And I actually left a slide out where we have, when you generate Mixed Phoenix Gen presence, it creates a my app presence module, which is empty by default, but that has a fetch callback, which is a ability to say, here's a diff of all these things that have happened, and you'll get a bunch of user IDs, and you can make a single query and then populate the metadata with extra data using in one place. So we have basically features in place to allow you to collapse all of those things into one event, and then we'll push that out as one broadcast.
Thanks for the talk. I was wondering if you had any contact with the authors of the paper, if they helped you the concepts.
No, and like I said, hopefully, I tried to make sure when I was rehearsing that I didn't put them down too much because I mean they did some amazing research, especially on their Delta-based CRDTs, which we've implemented. So if you fall behind, we don't have to send our entire CRDT back to you. We'll just send a snapshot in time of maybe 100 or 1,000 users and keep those around for a while. So if you fall behind, I can just send you the minimum amount of information and fall back to the tragic case of having to send my entire state. But no, we haven't had any contact with them, but really great work. So I think that it's just unfortunately I'm not an academic.
This CRDTs implementation is really cool. So my question is, can I use the CRTTs without the presence module? Is it separated somehow?
Yeah, so Phoenix Tracker is our lower level that presence sits on top of, and the tracker is doing the CRDT and the cluster membership. So there's a Phoenix Tracker state module on the Phoenix PubSub project, and that's the CRDT, and it's publicly documented. So yeah, you could use it. If you depend on Phoenix PubSub, you have a CRDT that you can put information into. As long as you have a process, you can attach data to it and use it just like we've talked about.
Let's keep your hands up.
Thanks for the talk. Yeah, when a user goes offline, you don't immediately, there's a certain delay. Are you batching those operations, or how does it work? And does the node limit we heard about yesterday also apply there?
Yeah, I mean, the node limit, so one thing we're doing is to do cluster membership, we're using a heartbeat protocol, which just means periodically, if we have information that has changed, we heartbeat more frequently, but we just send everyone a message periodically, which does not scale entirely well, but that's actually what the current Erlang distribution does, is they heartbeat. There are other protocols like, we were looking into Swim, which is another way to do cluster membership, but guarantee that you're not going to flood everyone with 1,000 messages. So if you have 1,000 nodes, you're not going to get 1,000 messages every second of where everyone's at. You can hit a subset. So there's actually a Swim branch on Phoenix PubSub, and I ended up saying that I think heartbeats are going to be good enough for now. Instead of trying to implement, I was excited after Jose was like, you can do this, and then I was like, yeah, I need more research papers. I can do some crazy stuff. But no, so I was like, since this is good enough for Erlang, and it's good enough for 50 to 100 nodes, we've pretty much said if someone hits a bottleneck with our heartbeat protocol, so maybe it's good for 40, 50 nodes, I'm not sure. You can sponsor Phoenix to support more because you're going to have millions and millions of active users. So, but did I answer your question? I forget the exact topic. Okay.
Super cool. I want to use it. But does presence handle clock corruption or consensus?
In corruption in what way?
So if I lie about what time it is, then I can kind of grab a hold of what the real state of the world is.
So
that's my understanding.
Unless if you lie about your vector clock, because there is no sense of time.
Yeah. I lie about my vector clock.
Yeah, I mean, in our system, we have trusted actors. So as far as Phoenix Tracker is concerned, there's a tracker running on every node that's sending the vector clock heartbeats. And if one of those starts lying, I say you have a serious problem, but it's not code that I wrote. So yeah, it's not a federated distributed consensus. So for us, as long as we've implemented this correctly, it should be conflict should be mathematically impossible. And as long as there's not some rogue commit that does some nefarious things. What's that?
Bad memory.
Or bad memory. Yeah, well, I mean, even from bad memory, yeah, it's okay, the bad memory case. Yeah, I don't know. Yeah, we're only using the vector clocks to determine unique pieces of information. So if that memory, or if that data in memory somehow changes, all bets are off. But I think that you have bigger issues. I mean, that applies for any parts of your program. So.
Last one.
Hi. So does the presence work only in a cluster, or could you deploy it to Heroku with probably currently Redis?
Yeah, so it works on, yeah, after I crapped on Redis so much, it works on Heroku with the Redis PubSub adapter. It just works with Redis. You deploy Redis and it works. It's going to be fast enough. No. Yeah, it's really neat that we were able to, Phoenix PubSub was a way for us to do distributed PubSub, but then we also wanted to be able to support people that couldn't run distributed Elixir. So we added the system for PubSub adapters. And then it was when we went to make presence, we were like, hey, we have this really nice way to send distributed messages across a cluster, and it would just happen to work on Heroku because we can build it on top of Phoenix PubSub. And then we made presence work, and then we were like, oh, we can actually build service discovery on this thing that we tried to, so it's these layers have just naturally kind of fallen out. But yeah, I did just work on Heroku today, even though just so everyone's clear, you should never, ever, ever use the Redis PubSub adapter if you can use distributed Elixir. There's no good reason to, unless you're forced to, because Heroku can't cluster dynos.
Thank you so much.